In this video, I want to pick off from where I left off in the last video. Recall we had these 5 parent trees growing in the forest, and from each parent tree, we got 1, 2, 3, 4, 5 seedlings. We developed a model for seedling height that looked like this. There's the J seedling height nested within the ith parent tree. It was equal to mu plus the parent tree plus the seedling effect. And we noticed when we made our initial plots that we had a bit of a problem. So this horizontal line here was the average of the 25 observed seedling heights, and it turned out to be 9.8. Now, based on the values that we used to simulate the data, we would have expected a value of 10, but we got pretty close. And this would be T2, the parental effect of the second tree, and this value here is the average of 5 seedling heights. Those would be the observed 5 seedling heights associated with the second tree. And you can see the problem is the discrepancy. Is that we don't know this. What we see is this. And there's clearly a discrepancy between the true value here and what we observed here. So the way we're going to get around this is we're going to use shrinkage to take this observed value and we're going to shrink it towards the mean. And in the last video, we compared a couple of scenarios, one in which the seedling effect was drawn from a population that was normal with mean 0 and standard deviation 7, and another in which it was drawn from a distribution that was normal with mean 0 and standard deviation 1, and that we saw that with a larger amount of variability, we were going to need to use more shrinkage. So that's where we're going to pick off today. And we're going to have a shrinkage factor that is calculated like this. And this shrinkage factor is really just, if you look at this expression here, it's just the proportion of variation that's due to the parent tree effect. So this is the total variation or total variability down here, and there's the parent tree effect. That would be the T effect of variability, and this would be the average seedling effect. Now, because we're dealing with an average seedling effect, and we know that when we're dealing with the variability or the variance of an average, that's going to be the standard error. So this expression here takes the variance of the seedling effect, divides by n is equal to 5, because that would be the variance of the average of 5 trees. The other thing you'll note is we've got these little hats, and these little hats are occurring because these values here, and here, and here, all these values are estimated. We don't know those. And that's why it's necessary to put some hats on them. So if we think about what we actually did and the numbers that we obtained, the value here was 4.0, which by chance is what we actually put in. This was 4.0. This would be 66, sample size of 5. Put that all together, and you get 0.235. So that's our shrinkage factor. And we're going to use that shrinkage factor to take our observed mean and shrink it towards the average mean. And the way we're going to do that is we're going to use the following formula. And the following formula is Z is going to be equal to SF times Y plus 1 minus SF times y bar. So, what are these things going to be? Z is going to be our shrunken mean, our new mean. SF is what we've got here. Y is going to be the observed average of the 5 trees associated with any one parent. And Y bar is going to be the overall average of 25 trees. So if we plug in some numbers, what we're going to see is Z is equal to 0.235 times the observed value of those 5 seedlings associated with the second tree was 4.2, plus this turns out to be 0.765 times Y bar, which was 9.8. And that's going to turn out to be a value of 8.5. But let's think about what we've got here. What we've got here is a weighted mean. We've got a weighted mean of 2 different things. We've got a weighted mean of Y and a weighted mean of Y bar. And what are the weights? The weights are a way of SF attached to Y, and you've got a weight of 1 minus SF attached to the overall average. So what you can see is that the shrunken mean, Z, which is equal to 8.5, is a weighted mean of 2 different means. 9.8, the overall average, and 4.2, the average of the 5 tree seedling heights that we observed. And these are our weights. 0.235 attached to Y, and 0.76 attached to Y bar. And the reason for that ratio, if you look at this 0.235, 0.76, you can see that it's attaching a particularly high weight on the overall mean, and that's just because of the fact that when you consider the total amount of variance, only a small amount, relatively speaking, 23%, was associated with the parent tree effect, and a relatively large amount was associated with the effect of the observed average seedling heights. Okay. And so we simulate those data, we plot them out, and here we see our tree 2. And here's our tree 2 right here. That's tree 2. And there's the value of tree 2 that we actually used when we simulated our data. This is the observed value of these 5 seedling heights. And then we've got right here our shrunken value. And you can see what's happened is that the observed value of the 5 seedling heights has been shrunken towards the overall mean. So I just went over one particular way of calculating a shrunken mean. There is another way, in fact there's many other ways to do this shrinkage thing. And the way that R does it is it uses the RANF function. So it's not going to use shrinkage. It's not going to do shrinkage using this kind of formula. It's going to use its own process that's implemented once you call on the RANF function. Now, the mathematics behind it is represented in this horrible looking thing, which I really don't understand at all. But if you remember the idea of mixed models in matrix form, and the notion is we have these G matrices and these R matrices, you can see that the shrinkage factor that's calculated using the RANF function is in fact going to consider the variability that's associated with the variability among the individual trees, as well as that would be associated with the individual seedlings. And so I simulated data for an additional 10 trees, a whole brand new simulation. And here we have the values of t that I would put in. Here we have the observed mean of the seedlings associated with term t. And here we have what are known as BLUPs. Sometimes they're capitalized. Stands for best linear unbiased predictors. And these are the estimates that are obtained when you use the RANF function in R.